Hey, so I had a video request come in for this guy, and this is actually kind of a fun problem, good example of mechanical advantages. So what we have here is we want to get the magnitude of the gripping force. So the gripping force is over here on the right-hand side of this machine. If we have two 400 Newton forces applied as shown, so we're squeezing the handles over here, and we're going to get a different force over on the other side. We've got some lever arms going on, and this will be an interesting, we can maybe look at with or without this member AC in the machine to see how this is helping out. The dimensions on here are a little bit tricky, and that's why I gave you guys this added figure here. So when you're looking at the direction of this AC force, we're going to grab this 30 millimeters right here, and then the base of this triangle, take it off of the bottom. So this 96, but it's not the entire 96. We've got this little 12 millimeters up here at the top. So sometimes you have to really study the dimensions of these things to figure out what's going on. Okay, I'll go ahead and do this in Excel. So let me pull over a blank worksheet here. What we're going to do is walk through it with the piece that we know the most about over to the side that we know the least about. So taking this guy, look at each solid piece of this individually. So here's our yellow handle, and we have a two-force member here in green. So we know this is in compression. And we know the direction of the force because it's a two-force member. And then here, this orange piece will be the last one that we do. So we have applied force, the two-force member, and it's kind of pivoting around this little pin B to have the gripping force over here on the other side. We're going to start with the yellow piece because we can actually solve for what's going on in this one, and we don't need to solve for the whole thing. Really what we need is AC, so this little two-force member. So if we take the moment around D for what's happening on this yellow piece, we can get what AC is here. So let me go ahead and copy over another diagram here. So we're going to start by just looking at piece AC. We don't actually have to solve for the forces acting at D. What we can do is take the moment around this pin and make sure that you have the dimensions right for this compression member coming down. Okay, so taking the moment around this guy, and I'm going to go ahead and copy over some moment tables here. And maybe I want to copy over what we're given in the problem statement. So I think you guys were given 400 newtons applied over here at the handle. I'm going to do something a little bit different again so that I'm not giving you the entire answer here. So we'll take the moment around D. So we're going from D to the handle, and then we have from D to that compressive member AC. Okay, so if we go D to the handle, that's going to be going over, we have this 30, 96, we're going in the negative direction. So we're going from D all the way to this gripping force. And in this case, the force is going upward in the J direction. So I'm going to just connect it over here. So later on, I can change the applied force, and all of this should update for the different scenario. Okay, so here is our first moment that is around D generated by this gripping force over here. When we get over here to AC, so again, we're going to go from D to AC, and pay attention to the dimensions here. So we're going to go negative 30 in the X direction, And then there is a little bit of a gap in the y direction too. So we're going to go up 6 millimeters. If you just keep everything in the same dimensions, it's okay to not have meters here. It'll cancel out at the end. Just be consistent through all of it. So we're going over 30 and up 6. And then for this one, so if you think about how this force is in here, so if we have the magnitude of the force, the x component, that would be 84 divided by the overall length of it, right? And then in the y direction, it would be negative, and the fraction of it in the y direction would be this guy. Okay, let me, so this would be the equation in here, and we want the moment to add to 0. So this is going to have to add together to the negative of what's happening here. So there's a little bit to crank through. You can use Excel Solver, or if you put this into Mathematica, so this is kind of what you would do by hand to solve for what AC is. So I'm going to put another little table up here where we're going to go ahead and solve for AC. I'm going to put those dimensions up here too. So the x dimension is equal to 96 minus 12. And I know that is 84, but I want to just leave that equation in there. So in the future, if I remember, why did I use 84? I can go back up here and remember where that I direction came from. And then the j component is 30, and the overall length of this thing. So let's get that. A squared plus B squared. Okay, so that would be, yeah, the overall length of this guy. If I plug this in, okay, so I have R cross F, where negative 36, so I'm just showing you how I did this in Mathematica, and then the force is going to be positive in the I direction, negative in the J direction, and this cross product needs to add up to this number here. So if you crank through the algebra on this thing, the magnitude of AC ends up being this. So I'm going to go ahead and put that in. So I'm going to say equals my moment times square root SQRT 221 divided by, okay, so if that is the magnitude of my AC, and let's make this positive, then I can actually fill in the x and y components. So my x component, that's going to be this, times the fraction in the x direction. That's kind of my little unit vector, how much is in the x direction. And my y component is going down, so I'm going to multiply this by the fraction in my y direction. Think of those as unit vectors. And just as a last check, so if I say equals x times y minus y times x, I'm going to get that positive 3,700. So that means I know that I got the right magnitude for my AC force. Okay, so now that we have this green member here, and we solved for that by just taking the moment around D, and it's, yeah, that's a little bit tricky. So walk through the cross product, or you can do the goal seek in Excel to solve for that. But that's going to be important. Let me go ahead and color code that one with green. That was a bright green. So this is going to be this member right here. So now let's go ahead and walk to the next piece of our structure. And that is to look at the forces happening on the handle over here. Okay, so we know AC coming up. We know the applied force pushing down. And the next little piece of it is we want to get the gripping force. So we're pushing down on a wire or something, but actually if we think about the forces acting on this orange piece itself, the wire is pushing up on the orange piece. And for this one, what we're going to do is take the moment around this pin B. That way we don't have to actually solve for the forces at B. What we're really after is the gripping force. And our mechanical advantage is going to be the difference between what we apply versus how much pressure it puts on here. Okay, so taking the moment around B, I can go ahead and copy my moments just to get some tables in here. So I'll go ahead, and for this one we're going from B to the applied force, from B to AC, and then from B to the gripping force. So we're going to have three moments that we have to add together here. So let's go to the left from B to the applied force. So that's going to be 120 plus 12 in the negative direction. And that applied force is negative over here. Going to link that over again. Okay, so there's our moment from the handle. That's going to be counterclockwise. Counterclockwise is positive. Okay, from B to AC, so this is going to be 120, negative 120. And AC is now pushing up. So it's pushing down on the handle, but we're going to take the opposite of what it was over here. Okay, so if we go through that moment, so here's the moment from AC, and what's left, this guy is going to have to balance it. So we're coming to the right, 36, and this will be going up in the Y direction, and it's going to have to balance the moment around B. So we'll say equals negative this plus this, and our force will be equal to this divided by that. Okay, so in this case, our gripping force would be 8,445 newtons, and we got there by applying 300 newtons. So if you look at comparing these two, force applied equals, so that was only 300 newtons, and by applying 300 newtons, we were able to get out of this thing force grip. So we can calculate our mechanical advantage here. So that gives us a mechanical advantage. It's calculated by what you get out of it divided by what you put into it. So wow, 28 times the force that you put into it. That is very impressive, right? That's really impressive. What would happen if I did not have AC in here? What would happen to this? If I made this 0, it doesn't work. So think through this intermediate member and why you would design it this way. And this is a very nice mechanical advantage for a small, like if you did that with straight lever arms, it would have to be a huge, huge handle. But instead of making a huge long handle, we can put this intermediate member in here, and that will give us the same effect. So very, very clever design for this set of pliers.